So this lecture has 3 sections of different lengths. The first one is about nonlinear issues. You typically have a fluid dynamics equation that the velocity field is a function of the velocity field, and you might be interested in the steady states. On the whole, I personally solve an initial value problem. I start from rest or start from some state, and I integrate in time until it gets steady, because there might not be a steady solution. And I'd find out if I solved a time-dependent problem. It may be the steady solution you find is unstable. So if I try and find it by integrating forward in time, I wouldn't find it, and then I would have learned something. However, you sometimes do want to find the steady state, and probably the steady state as you vary the Reynolds number or some parameter. So this is about finding steady states. Obviously, this is not the partial differential equation, but the discrete version by some method or other. You're trying to find where does that vanish, and one can use Newton iteration. When it converges very fast. When it doesn't converge, but it might not converge. So the idea is you have some approximate solution and you add a little bit to it to get the new approximation, and you would rather like the this little bit times the derivative of this function to equal the value that you're failing to get to 0. So standard Newton iteration, other than the derivative is, of course, the derivative of the velocity field with respect to this function of the time derivative with respect to the velocity field. So it's a very high dimensional matrix called the Jacobian matrix. And it's an interesting matrix because it tells you about the stability of the system. So if all of the eigenvalues of this Jacobian matrix F primed have a negative real part, the system is stable. So this has got an error in it. This should not be text, but test. And the X should be an S. So you can test whether all of the eigenvalues of a big matrix have a negative real part. Is it a stable system? Without finding them all. You look at a sequence of determinants, and there's a criterion that will tell you if it's a stable system without finding all the eigenvalues. But the eigenvalues are interesting. So there's a question, how do I find this derivative, the Jacobian matrix? Very occasionally, you can find it analytically before the discretization. But normally, you have a discretization F, and then you want to take its derivative, and you end up doing this by numerical differentiation. You look in the direction of some vector, you move a small distance along it, you see the difference of the function in that direction, and divide by the change. So primitive differentiation, and there is an art to make sure h is big enough, but it's not too big. There is a way that when you are doing the Newton iteration, you do know something about the curvature of the function, and you can use that to update the derivative from the previous derivative. So if you have some approximation to the derivative in some important directions, and then you make a Newton iteration, you can update the derivative by this formula. The derivative shouldn't change all that much, so it's probably not worth doing this. Okay, so here's a little example. I rather like the nonlinear oscillator called the Van der Pol oscillator. It has friction of u squared minus 1. So when the amplitude of the oscillation is small, it is undamping. It has minus 1. So the amplitude grows. When the amplitude is very big, you have a lot of damping, so the amplitude decreases. So there is an equilibrium amplitude, and the answer is 2. Although the oscillation could be highly nonlinear if the parameter friction parameter is small, then it tends to be cosine t. If the friction parameter mu is very big, it tends to be a very nonlinear oscillation. It slides from 2 to 1 and then flips to -2 and slides to -1 and then flips to 2. It's a very nonlinear sawtooth oscillation. So you would like to find this steady oscillation, the finite amplitude oscillation, that's a steady state. So it's not a steady state, it's a time-dependent state because it's oscillating. But anyway, we'd like to find the steady oscillation, and this is how you can do it. It's a case where we can analytically find the Jacobian, sort of. So you're searching for a solution that after a period t, you get back to the same value and the same time derivative. So you have an approximation, and for the time-dependent solution, an approximation for the period, and you contemplate nearby the period being a little different and nearby solutions. The V, because this is a small parameter, satisfies a linearized equation. So this is the Jacobian, and I can arbitrarily start the solution for the little perturbation as starting with 0 amplitude and velocity 1, because it's all in the normalization of how big is epsilon. So what I do is I integrate the original equation and this for the perturbation round to capital T, and then I say, if I evaluate it at Tn plus delta, what do I'd rather like the solution at that time, which will be the solution at Tn plus a contribution from the little displacement here that I don't know, plus this perturbation here, ought to be equal to the starting value, and the starting value has been set to 0. And similarly for the velocity. So I end up with two equations for the unknowns, how much amplitude of this I want and how much stretch of the time period I want. So then I've got a correction, and then I can add that and do another iteration. But this is a Newton-Raphson iteration to try and find the period and the form of the nonlinear oscillator. In a case where I can analytically find the Jacobian, other than I do have to integrate numerically this equation in time and this linear equation in time. Okay, so as I said, you may be looking for the steady state for a whole sequence of different Reynolds numbers. So there's some parameter, alpha, the Reynolds number, and I've got one solution. How do I find quickly the steady state for the next Reynolds number? And you do it by saying I have a solution for the value of the parameter alpha naught. The solution is u naught. And I'll make a small increment to a new value of the parameter of alpha naught plus delta alpha. And there is an unknown or new solution, u naught plus delta u. And then I put this and say that not only does f have to be 0 for u naught, f has to be 0 for u naught plus delta, and linearize. And you see I get, how does the function f depend on the parameter alpha, and how does the function depend on u? And it's the same Jacobian matrix gets involved. So I can therefore, if you say how much you want to increase the Reynolds number, I can find out how the solution changes by solving that. And everything goes on quite well until when the Jacobian matrix here becomes singular. And when the Jacobian matrix becomes singular, it's telling you your solution has gone unstable. And there's a series of things, so it becomes unstable at that particular value of alpha, and there's a whole series of things that can happen. So the first one is that the solution which you were following, you had a solution you were following as alpha changes, finding just nearby solutions, suddenly you arrive at this point where the Jacobian vanishes, and it's telling you there's a bifurcation, that some new solutions have arrived. So while there's an eigenvalue, The Jacobian is singular. That means there is an eigenvalue of the matrix which is 0, an eigenvalue 0. The eigenvectors tell you the directions of the new solutions. So the eigenvectors tell you where to go looking for new family of solutions. If you want to keep on this solution, which will be unstable, is you can jump over it by taking a big jump in delta alpha. Okay, so one thing is there might be a bifurcation. Another thing is there might be a turning point, that you're following the solution along and suddenly the solution turns back. That there aren't any solutions beyond a certain alpha. But there are two branches, the branch you started on, and then there's a second higher branch. And the way to tackle that sort of problem is that this is not a very nice curve with an infinite gradient. But if you reflect around 45 degrees, you get a curve which has a maximum. So why don't you plot alpha as a function of the size of u, rather than plotting the size of u as a function of alpha? And then you get you can go away, get rid of this turning point question. And then the really awkward thing can happen to you. You're running along the solution, and the solution suddenly stops, and there's no other solution nearby. It's quite unusual, but it does happen. And what happens there is the solution has lost its stability and there are no other stable solutions around. Everything around you is totally unstable. Okay. Another issue is searching for singularities of physical systems. So if you take potential flow round a sphere, potential flow around the cylinder, you know how the tangential velocity is increasing to the extremity, and then it starts to slow down towards the rear stagnation point. You can take the boundary layer equations and integrate the boundary layer equations, and the boundary layer equations are very happy going up to the maximum velocity, and they go a little beyond. I think it's to 104 degrees, but I'm not sure. And then the boundary layer equations blow up. Of course, the real fluid equations mean that there's a detached, the boundary layer takes off into the interior and there's an attached wake region. But that's not within the boundary layer equations. And the outer flow is no longer potential flow round a cylinder. But we're quite interested in where does that happen, that singularity. There's another singularity in viscid flow. If you have a vortex sheet, a Kelvin-Helmholtz instability, then there's not an infinity of the solution, but the interface develops an infinite curvature in a finite time. And there are people who are very interested in singularities in finite times. So how do you tackle these? Well, the naive thing to do is to start taking smaller time steps, smaller space resolution, clustering points around the dangerous area. And all you do is you postpone the singularity. There's a singularity there, and you can get closer and closer to it, but you'll never get there. And you won't quite ever know what you're doing. And it's a good idea if you know it's a good idea if you know what sort of singularity you're dealing with. So if I've got a singularity at some time, you can see the answer getting bigger and bigger and bigger. You'll never get to infinity on a finite computer. But suppose you knew the solution had a square root approach to infinity. So at some stopping time Ts, it behaves like 1 upon the time to the stopping time. Then what you want to do is to plot 1 upon the amplitude. Oh, you probably don't know what the stopping time is, but you know it has this behavior. But if you plot 1 upon the amplitude squared, you're looking at a linear line, which you can extrapolate down to where 1 upon the amplitude is 0, and you found the stopping time, without going all the way up the curve to infinity. You finding out where this stopping time is, looking at the curve that's getting bigger and bigger, is very difficult. But this is very easy to find out, to extrapolate. So, little diversion. I showed this curve earlier. At the end of the first section, we had a method for calculating the force on the driven cavity. And I pointed out that it was designed to find the steady state. It was hopeless at finding the initial value, initial behavior. The initial behavior, the force ought to be 1 upon 2 the square root of pi, 1 upon the square root of time. So what I did, which was bad, is I actually multiplied by the square root of time and plotted that as a function of time. So this is the force times the square root of time. And you see as I try to get to t equals 0, my solutions blow up. So had I listened to myself now, when I was plotting that, what I would have plotted is 1 upon the force squared, which is what I did 10 minutes ago. And you see the curves are beautiful. You can see that all the curves are nicely behaving. As we go to time equals 0, 1 upon the force is going to 0, therefore the force is going to infinity. And this is the prediction of this. And you can see these curves, I've not quite got early enough, but they're clearly tangential to this line. So there's another way of searching for singularities, which you use computers, but use computers not to do arithmetic, but to do algebra. So you can sometimes give your governing equations, substitute a power series in, and find the solution. So you'd find the coefficients from your governing equations. And then if you think there's a singularity at some stopping time, which is a 1 upon alpha to 1 upon the power alpha behavior, then it turns out that the ratio of the coefficients is equal to 1 upon the stopping time, and then 1 minus 1 upon n. And you can find out from this expression, if you vary n, what is alpha and what is the stopping time. So that's a way of finding the nearest singularity. It finds the nearest singularity in the complex plane. So in most problems where the solution blows up, it blows the nearest singularity in the complex t plane. This is for complex t. We only deal with real time, but you have to think about the complex plane. The nearest one's on the real axis. But there are problems elsewhere. And then there's another way of tackling this, is to rephrase the power series in t as a power series in t divided by a power series in t. You go to half the, instead of going to n, you go to n upon 2 and n upon 2 typically, and they'll tell you where there's a singularity. So sometimes the singularity is a square root singularity. This can only give you pole singularities, and you find there's a whole series of poles along an axis, which is telling you there's a cut in the complex plane corresponding to a square root or logarithmic singularity. So associated with singularities and the exercises that you've done, was it an optional one to do the driven cavity with a uniform velocity along the top with different values of n? And you find the force increases as you increase with n. What is very interesting is to take your data of how the force is varying with n and plot it against log n. And you'll find a beautiful straight line for the force. It is because the stress in the corner is 1 upon r, and if you integrate 1 upon r, you will get what 1 upon delta x, the log of 1 upon delta x, the smallest value of r you've got. So plot your, in the case of a uniform velocity along the top, you've got the force increasing, plot the force as a function of log n. First bit. Second bit. Wavelets. Okay, wavelets are a way of compressing data, either audio signals or visual signals, pictures. In fluid mechanics, they have been used very interestingly to study turbulence. So you can analyze turbulence. People have promised to use this so you use it to represent audio data or visual images, and it compresses the data. Where there's boring things happen, it represents it very easily. Where there's interesting things happen, it concentrates on representing it well there. So it's an economical way of representing the audio signal or the image. You can analyze turbulence and you'll find that 95% of the things are boring and there's a 5% which is very interesting. And people have thought, could we use that representation of the 5% that's interesting as an efficient way of computing forward? They've promised it and it's not been delivered yet. And it's a good idea and it may not work. Okay, so the contrast is between finite differences, which are local, and spectral representations, which are global. Finite differences are very good at representing discontinuities, because that's all they are. They're very poor at representing waves. You need quite a number of points, at least 8 points, to represent one wave, and you probably need 40 points to represent it with any accuracy. Spectral methods, Fourier analysis, are very good at representing waves. You just want 1 or 2 or 3 of them. They're pretty bad at representing discontinuities. And then so if you have a discontinuity, the Fourier amplitudes decay like 1 upon k. And that's a warning that the turbulent spectrum, the Kolmogorov spectrum, which decays like k to the minus 5/3, does not mean there are eddies of each size there. Some people say there are eddies within eddies within eddies, the Richardson argument, and it's rubbish. I don't believe in inertial cascade. I do believe in the inverse cascade in 2 dimensions, because you can actually see the eddies of different sizes. Okay, so that's a personal view of turbulence. Okay, so wavelets are a combination of the good things of the two. They're localized, but they're waves. And just think about a musical tune. What is a musical tune? It's a sequence of notes of different frequencies and different amplitudes. The Fourier analysis of that is bad because it doesn't see the finite duration of each frequency. The finite differences means you've got to represent at least 8 points, and the typical note is probably a few hundred oscillations of that frequency. So the musical score is very economical. You just say there's this list of sequencing times of notes of different lengths, of different amplitudes, of different frequencies. And the wavelets are rather like that. Okay, so here's 2 possible. There's more than a dozen possible ones. Morley was introduced to look at seismographs, which are wiggles, but they are localized. And David Marr, who I happen to have known, was interested in pulses, electrical pulses in the brain. And he has the Mexican top hat, as it's called. So it's 2 derivatives of a Gaussian. So this is the real and imaginary parts of that, and this is 2 derivatives of a Gaussian. They decay very rapidly in space. They decay very rapidly in Fourier space. You can make things identically 0 in space, outside a finite interval, but then they don't decay very well in Fourier space. Equally, you can't have things dead 0 of compact support in Fourier and real space simultaneously. So you want them to decay quite well in both of them. Now, like the Fourier transform, the continuous Fourier transform, there is a continuous wavelet transform. So we first have to get some wavelets. So, there is a function, a universal function that defines the family of wavelets. And you generate the whole family by having translations of this function, called the mother wavelength. You translate the mother length through a distance b, and you stretch the scale by a. and then there's this little 1 upon the square root of a outside, which is to make sure the integral of psi squared, it remains 1 in its stretched forms. Okay, so there's this family of wavelets defined by the basic form, the mother wavelet form, and then if you multiply that times your function and integrate with respect to x, you get the AB wavelet component of this function. As a complex conjugate there. And then there is an inverse transform, just like there's an inverse Fourier transform, which is you take your components, multiply by the exactly the same function, and and integrate over the various translations and various stretch rescalings. And there's a coefficient, instead of 1 upon 2 pi, there's something which is the mother wavelet's Fourier transform squared divided by k integrated. And this integral here only exists if this vanishes at k equals. So that s should be k. That s should be k. Correction. That's true, yes. Sorry about that. So if you want the Fourier transform at k equals 0 to vanish, you're asking for the average value of the wavelet function to vanish. And it's a good idea not only the average value to vanish, but also quite a number of the moments, the first, second moments. So that makes it nice. Okay, so that's the continuous wavelet. You want a discretized version because you have finite number of data points. So it's just, and we had this before, we had the continuous Fourier transform, and we had a discretized Fourier transform. And there is the same thing again here, a discretized wavelet transform. So we want to deal with points, and I'm dealing on a circle, so it's fully periodic. And they're going to be equispaced, and the number of points wants to be a power of 2, because I'm going to cut the interval into 2, then I'm going to cut it into quarters, into eighths, etc. I keep on dividing the interval by 2, so I need the number of points to be 2 to the power of something. And now we take the mother wavelet form, the function psi of x, and we stretch it, and in the discrete world, we stretch it and we translate it. We translate it by integer amounts, and we have a sequence of stretches which are frequency doubling. So we only have a few frequencies, and they are double, quadruple frequency doubling. Okay, so you can think of there being one wavelet over the whole interval. The mother wave, it exists over the whole interval, and so that would be with I equal to 0 and j equal to 0, and it will cover the whole interval. Then we go up to an I equals 1, where we've stretched it, and we need 2 of them. We need one that deals with the first half interval and one that deals with the second half of the interval. So there, in the second case, we need a shift of 1, j equals 1. And then we go down to the next one where there are 4 intervals, and there will be, these will be the psi I equals 2, the psi 2 modes, and there will be a psi 2, 0, 2, 1, 2, 2, 2, 3. I have 4 of them dealing with the 4-quarter interval. All the way down to the finest level, where there will be 2 to the power n minus 1 subintervals. So this is what's called a multi-scale representation. Big buzzword. So the discrete wavelet transformation is just to multiply these discrete wavelets with the frequency doubling and integer shifts times the function and sum over over these equispace points with the data on the equispace points, and we get the discrete wavelet component of the function f. And you can work out that while the base one involves a sum of n terms, because the subsequent ones really are involved in half intervals. There's two of them at n upon 2, and then when we get to the quarter level, there's 4 of them, but they only involve n upon 4 points. And the sum of the operations is therefore n log n. So to work out the discrete wavelet transformation, it's an n log n operation. It's not n squared. That's really exploiting this sort of localization. There are some orthogonal wavelet systems. That's a very special psi of x. The mother wavelet has to be rather special. And there are, moreover, orthogonal wavelets for the discrete world. And they would have the property, the sum of two of them are just delta functions. When you have an orthogonal system, then the inverse transform is the obvious thing. You can get back to your function by summing over the wavelet components times the wavelet functions. And there's a list of some of the wavelet functions. Okay. Now, find the discrete wavelet transformation is an n log n operation. And the nice thing is there is a fast discrete wavelet transformation, which only is order n, rather than n log n. Not much of an advantage. So it's very difficult to explain this unless you take a course of pure mathematics for several weeks. So I'm going to try and explain it, and I'm going to do it first in terms of the simplest possible wavelet, which is pretty useless wavelet in practice, and then move over to what happens in real life. And the final answer is use a MATLAB workbox. They're in MATLAB. So this is the background of what MATLAB is doing. Okay, there's the HAR wavelet, which vanishes outside an interval, and inside the interval it's +1 for the first half and -1 for the second half. Okay, so it's just one square wave before going to 0. So this is sort of finite differencing, which I said was a bad idea. That's why it's a bad idea. I'd like a smooth function. But anyway, and I'm going to work it out with just 8 points, because I can then write out everything with 8 points. So the base one happens to be 1 upon n, a sum of the sum of the first 4 points, take away the data at the next 4 points. On the first half interval, it is the sum of the first 2 points, take away the second and third points, or 4 and 5, take away 5 and 6. And then we're at the finest level, it's the difference between adjacent ones. That's because of this step function is +1 or -1. And there are the stretching coefficients in there. So there are 2 problems with this, which if we recognize there are problems, we can learn from. One is this doesn't represent the mean value, because I have the difference between the first 4. Everything's a difference. So the mean value is not there. That's because there are not 7 points, but there are 8 points, and I only have 7 variables here. So I need one more thing. And the other thing is you can see there's repetition, that I add 0 and 1 together twice. I add 2 and 3 together twice, etc. And when I go beyond 8 points, there's even more duplication. And that's how we get out of this n log n, and push it down to n, is we find a way of not doing the duplication. And it goes like this. Firstly, we have to introduce a new object, a new component but it's not f00, but it's f00 with a capital phi up there to say it's not associated with the psi wavelet, it's something else, and it is the sum of all of them. Now I've got the sum of all of them, I can do everything. And then the inversion works. And I'm testing that out on one point. And what I need really is a new function associated with the wavelet. There's a thing called the scaling function. So the scaling function for the Haar wavelet is naught everywhere except for the key interval where it's +1 all the way along. And this scaling function has the same, it's the mother scaling function, and it generates the a family of scaling functions which have integer shifts and frequency doubles. So I have phi ij in the same way as the wavelets. And I can work out the components with respect to these phi ij's as being phi ij's with a capital phi at the top as just being a sum over the data points. So it's a parallel to the wavelets. There's a scaling function going on. Then this is the way the fast transform works, is you start at the finest level, which is only for the wavelet component, it just involves the difference between the adjacent terms. And then if we apply not the wavelet function, but the scaling function, we get the sum of the two. And we store that component. And we do it for all of the i's. So this would be for 0, 1, 2, 3. Then we go the next level up, and we can calculate the wavelet component out of taking the difference of these two from 0 and 1. And we calculate also the scaling function for this component as being the sum of those two. And then we go all the way up to the top. So all of those duplicated sums get pushed into calculating it once and then using it when you get to the next level. So the cost is a mere 4n operations rather than n log n. And the inverse transform is you start at the coarsest level. You're supposed to, at the coarsest level, to know all the wavelet components and to know the scaling function 0, 0. So that's 7 components and the 8th one as being the average value. And you can construct the wavelet at the first level down as being the sum of those and the difference. And I go one level down and I can at a finer level, I use the coarser information of the wavelet and the scaling function. And then I get down to the very finest level where I'm using the phi's that I've been calculating on the way down, the scaling function components I've been calculating all the way down, and I add it to the wavelet or subtract the wavelet to get the data points at the lowest level. And that's an order n calculation. Now, the interesting thing is in this calculation of the components and equally the inverse transform to get from the components back to the data, I didn't use the function. All I used are these coefficients, 1 upon the square root of 2 with plus or minus signs. And that's the key to go from this simple wavelet, the Haar wavelet, to any other more complicated wavelets. There are these what are called filter coefficients. So you just have to know the filter coefficients associated with that wavelet, and then you use the filter coefficients. And there might be a function there, but who cares? What is happening here is at the Lth, there's a red L there, at the Lth stage, the sum of the scaling functions times their coefficients up to the value L have all the coarse information, while the sum of the, so this is from 0 to L, I think it should up be to L. And J should go to 2L minus 1. So J goes to... No, okay, so this is a fixed red L. So there's a fixed red L. I'm summing all over the J. I'm summing over all the translations at some level of coarseness L. The scaling functions times the scaling function coefficient. And here I'm looking at all of the... so it's for all the J and all the I bigger than L. So this means all the wavelets of finer detail are here. So we're split at some stage, the fine scale data in the wavelets and the coarse data in the scaling functions. And that's why in signal processing, this is called a bank of frequency filters. We've got a way of there's a, whatever it is, a high pass filter that's giving us the high frequencies, and a low pass frequency that's giving us the low frequencies. And then we take this signal and then do another frequency cut to take out L, to put it down there, and put less than L up there. So there's a whole sequence of frequent high and low pairs of high and low frequency filters. Right. So the one that people use is not HAR, but is Dobesh's wavelet, which is defined by some horrible expression. And it has filter coefficients H0, H1, H2, H3. So this is D2. I think this one is the wavelet, and this one is the scaling function. I think they're non-differentiable functions. Everywhere the derivative doesn't exist. Why are we representing the signal in terms of this nonsense? So the good news is if you go up to D8, it looks much smoother. But then you have more terms involved. And then the really good news is that there's a toolbox in MATLAB. So now you know what the toolbox is doing for you. Don't try and program this. So very often in fluid mechanics, we're interested in particles moving in the fluid or something like that. And then there's a whole series starting with molecular level going down to meter cubes of fluid moving around. So the simplest thing is molecular dynamics. That's non-quantum in molecular dynamics. Very much used, you just integrate Newton's equations of motion for atoms flying around with van der Waals forces between them. There are clever techniques of tabulating the van der Waals forces and using tabulated data rather than calculating complicated functions at each time step. You typically have constraints that two atoms are stuck together as a diatom. And that constraint has to be maintained in your dynamics. And there's a process called shake, which constrains it for the half step, and rattle, which constrains it for the full step. And you use symplectic integrators. So I did write down a symplectic integrator, which is the one they use. The next idea down is lattice gases. Why am I doing this so numerically? The molecular dynamics does do dynamics with molecules atoms flying in all three directions, all possible directions. Some very nice studies, probably in the 70s, where people were able to calculate the viscosity of a liquid. Viscosity of gas, they're sort of theories for, 19th century theories virtually. But to actually numerically simulate molecules densely in liquid, you could then calculate the viscosity of the liquid. Okay, so going back to more a gas, people have played gas dynamics on a lattice. So the molecules are only allowed to move along the lattice directions, and they're only allowed to have one speed. It's a good idea to put the diagonals in as well, as where they're going to route 2 as fast. So every time step you move from one grid point to another grid point. And then you have collision rules. So if they come in like this, they could go out like that. If they come in like this, they could go like that. And if 3 of them come together, then what happens? And there's a whole series of collision rules. And you can actually, someone did burn a silicon chip with all of these rules put in, and you could parallel process it very nicely. So the problem with lattice gases, a reason, I thought it was nonsense doing this, but someone pointed out to me that if you work out what is the Reynolds number using the velocity of sound in a gas, the length scale you put in to get the Reynolds number is 1, is the mean free path. It's just what physics does. So if your length scale, your smallest length scale is the mean free path, why are you doing continuum mechanics? Why aren't you doing molecular collisions? So that's the reason why it might be a good idea to do lattice gas. The problem is they're very noisy. You've got one particle doing this, one particle doing that. So when you form an average over n particles, you get fluctuations of size 1 upon the square root of n. So with 10,000 particles, you can get 1% accuracy. If you wanted more than that, you're into 1,000,000 particles. It just 1 upon the square root of n is very slow to decrease the fluctuations. So the clever idea was lattice-Boltzmann, which instead of having atoms coming along the grid points, we know the probability, the fraction of particles coming along the grid point. And there's a different fraction coming this way and a different fraction coming this way. And then we know the Boltzmann distribution in equilibrium. So we ask, this is the fudge. So the fudge is we don't do real collisions now. The fudge is we modify the proportion coming in this direction with that speed towards by saying it relaxes in a time equation towards the equilibrium that it ought to have there. So there's this artificial simple that the probability distribution will relax in a linear equation, ordinary differential equation, exponentially to the equilibrium. And that equilibrium, that time constant, gives you the viscosity. 2 components of velocity, 3 unknowns, you need 9 variables. And in 3 dimensions, to represent 4 variables, I think you need a minimum of 15 in order to get the viscosity isotropic, whatever that means. Okay, next level up is Stokesian dynamics, which John Brady at Caltech nicely pioneered. This is in Stokes flow. In colloids, we've got lots of particles. There is a long range 1 upon r interaction. And the way to handle this is to first evaluate the so-called mobility matrix. That's the mobility matrix tells you how fast you move by applying a force. And that can be done, the mobility matrix can be done by pairwise additive. You just add, for the long range interactions, you just add linearly, this one interacts with me, this one interacts with me, this one interacts with me, just as isolated pairs of particles. That's theoretically the correct thing to do in the far field. And then for the near field, you look at the resistance matrix, which tells you what the force is for a given velocity. And we use lubrication theory. For near field, they're nearly touching, so we can use lubrication theory. In fact, we can use lubrication theory for very close, and we know the exact solution for any separation. We do use pairwise additive. It's quite correct when it's lubrication really close, because there's not a third one in the way. And you add up all the pairwise interactions. So now you've got the far field pairwise additive in mobility, the near field pairwise additive in resistance, and you duplicated yourself, so you have to subtract the duplication. And it sort of works quite well. And you can add Brownian motion to that by adding random bashes to the particles, we get a Langevin equation, and work out the diffusivity of particles in a colloidal suspension. There's a thing called Brownian fields I won't talk about. It's more, that's for viscoelastic flow. Right, there is something called dissipative particle hydrodynamics. Please don't do it. It's misconceived. It's based on artificial physics. It's not right in any form, ever. Right. What is, okay, so they're crazy physicists who are crazy, who did that. Okay, well, what is acceptable is forced couple, the forced couple method by Martin Maxey. And there, this is what you should do for particles, not at low Reynolds number in Stokes, but at Reynolds number of moderate 10. So suspensions of bigger particles. And you apply a series of forces inside. So you replace the fluid and the particles by pseudo-fluid everywhere and solve the Navier-Stokes equation everywhere. And where there are particles, you add extra forces. And the game of these extra forces is to make sure the particle remains rigid. So if the flow is trying to squash it, you apply opposite forces. So these are squidgy particles, but what you ask is that on average, the stretching of the particle is 0. So if the two particles are interacting and there's some separation, and you ask the average stretching of this one caused by this one is the integral of it is 0, then that's good. The problem is when they get very close and there's localized squashing of the particle near the contact but not elsewhere, this squashy particle approach doesn't quite work so well. Okay. I've been involved in simulating granular flow, the flow of a pile of sand, bucket of sand, and for that we do molecular dynamics. We actually solve Newton's equation of motion for each grain of sand, and 10,000 grains of sand at least, using really molecular dynamics. And there's an awkward issue of contact forces. They tend to be not van der Waals forces, but whenever the two grains come together, if they want to pass through into one another, there's a normal force against them, and there are tangential forces, friction forces. Because there are friction forces, it's not like molecular dynamics. You slowly lose energy. It's true in granular flows. You lose energy unless you feed energy in by shaking it or letting it roll downhill. And finally, there is a method called soft particle hydrodynamics, where you take the fluid domain and you make it into blocks, which you call particles, and you try to solve the equation of motion for moving particles, which just happen to be blocks of fluid. So this is very, very good. So firstly, this is a gridless method. There's no grid around, no mesh. So if you're studying a water wave which is breaking, there's no trouble about, firstly you had a flat, distorted, and then you've enclosed a pocket of air. It's gridless, you don't have to worry about what's happening there. It's very good on inertia, because it just says following this block, it's accelerated according to the forces. The problem is, with this method, the forces. You get forces from pressure, you get forces from friction, viscosity, and the way you calculate the pressure interactions and the viscous interactions is pretty ropey. It's not as good as first order delta X accuracy. Okay. But it is used. If you go and see in the cinema these animated cases of a big tidal wave gobbling up the important cartoon characters, that's all done by soft particle hydrodynamics. Okay, so I didn't give you any technical things, and that's probably easier, just over time. So I hope the important bit about this course was to give you my philosophy of how to generate numerically answers which are reliable. Make sure you've done enough iterations. Make sure you're at steady state. Make sure you've got the spatial and time accuracy. And worry about stability, obviously. So the philosophy is important. The first part of the course, I see from what you've handed in, it seems to have been successful. You ought to be confident you can solve simple problems immediately, within a day. That's fantastic. You're really very clever. Okay. The second part of the course has told you you can do more sophisticated things whenever you need it. There are more accurate ways, more refined ways, alternatives are available there and not so difficult to understand. The third part of the course is been a whole sequence of very brief glimpses of rather sophisticated things going on in specialized areas, and you may never need any of them. If you ever need one, you know it exists now. You don't really understand what's going on. You're going to have to read it up. But it's an exposure to, there are a wide number of things out there, and there are things I've not talked about, like turbulence, and I don't want to talk about the weather prediction. It has its special modes. Okay. The course has been, you've got the handouts. I should warn you that there is a continuous text of sentences, for most of it, in draft. And my wife insists it's got to be done by Easter. I get this draft to a publisher. So they may be quite soon. I've given one copy. If you really are desperate, you can see. But there are issues of copyright, so I'm not going to broadcast this. Okay, so the final thing is I have to thank you for being a fantastic audience. You've tolerated my English. I know my English is not Indian English, so it's a bit strange. You've not complained about that. Thank you. You're all very bright and attentive. Everyone's been paying attention. No one's been reading their emails or anything like that. Very good. Thank you. You're always happy and smiling. That reflects on me. I quite enjoy doing it when you do this. You've asked some jolly good questions that have helped me to explain better what I didn't explain properly. And I've really enjoyed you all. So teaching this course, it's been excellent. So thank you all. Thank you.